Okay, hello everyone, welcome to our meetup. So today we have Jinpeng Zhang, he's the head of TiDB storage team. He will be talking about how TiDB keeps performance predictable and a high load. Okay, I'll stop sharing my screen.
Thank you, Chen Hao.
Okay. Yeah.
You see my screen?
Yes, I can.
Okay. Okay, hello everyone. Thank you for coming and in person and online. And I'm Jinpeng, the leader of TiDB storage team. And today I'm going to share how TiDB keeps predictable performance under high load. Yeah. And before we dive into today's topic, I'd like to have a small interaction. And is there any open source developer or anyone have contributed to open source project?
Yeah.
Okay. As an open source developer, how to introduce yourself in 10 seconds? Do you mind to have a try?
Maybe at least a few projects I involved,
Okay.
or show my GitHub log.
Mm-hmm. Okay.
Yeah.
Okay, there is a more cool way to introduce yourself if you are an open source developer. Yeah, you just input your GitHub ID here, and they will be give you a really deep insight for you, like what kind of language you use and what activity you have done in the past few years, like issue, pull request, and what project you have contributed. Yeah, this project is OSS Insight. Yeah, you may curious about what is OSS Insight. Yeah, it's open source software insight. It's powered by TiDB Cloud. And GitHub is a very famous open source software platform. There are millions of open source projects here, and you can contribute to the open source project here. And we build a real-time pipe to grab the GitHub events from GitHub and store them into our TiDB. I mean, a TiDB cluster. And then we can do query on this database, like you input your GitHub ID or input the project you are interested, and then it will give you a real deep insight for this project or these people. Yeah, it's interesting. Yeah, you can have a try. It's cost you 10. It's cost you 0 cent. Yeah. Okay, let's move back to our today's topic, and this is today's agenda. And at first, I will introduce predictable performance really matters in real world. And the second part, I will introduce some like experience or some issues we have faced when we build our distributed database, TiDB. Yeah, I like to see it's not an easy job. Yeah. And the third part, I will introduce how TiDB to resolve all of these issues and how TiDB facing all of these challenges, like we introduce like load-based split and smooth background outlook, blah, 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 like that, and to produce predictable performance. And at the last, I'd like to introduce the future work of TiDB. Yeah. Okay, let's move to the first part. predictable performance matters. Yeah, this is a picture quote from the CS DynamoDB paper. Yeah, there's a sentence that another critical requirement for Dynamo was predictable performance, so that applications could provide a consistent experience to their users. Yeah. As a SQL distributed database, TiDB has a broad adoptions. There are more than 2,000 production adopters, and these adopters may across several industries like online shopping, insurance, and online gaming, even the manufacturer. Yeah, and also some important bank or cryptocurrency exchange. Yeah, so TiDB support so many different kinds of applications. Yeah, you don't want your application experiments unpredictable, like latency, performance. Yeah, so predictable performance really matters, especially for a SQL database. And this picture is quote from the CS VLDB TAOBench paper. This paper is wrote by UC Berkeley. Yeah, and in this paper, the authors test 5 different distributed SQL database, and TiDB, you can see TiDB gained a fairly great both in the latency and in the throughput. Yeah. So how TiDB can achieve this? Yeah. Before we dive into how TiDB can achieve the predictable performance, we'd like to introduce some real issue we have faced in past few years when we build our distributed SQL database TiDB. Yeah, I'd like to see it's not easy. Yeah, the first issue we faced is the traffic school issue. Before you build a distributed system, you may have a hypothesis that the request or the traffic may be even distribution, has an even distribution, the characteristic. But in real world, the most case is that the traffic school is the most case. Your workload more or less have skill issue. Yeah. If there is a skill issue in your distributed system, you may face that one or few nodes will overload it in CPU or in I/O, and this will result in the high latency for your service. And the second challenge we face is the background job may impact the foreground jobs. I mean, if the background job is too many resources, like CPU, like I/O, PS, or boundwise, yeah, and it will make the online request have a high tail latency. For example, in this picture, the yellow part denotes the foreground task like users write, and the red, that part denotes the background write like connection DC or other large events like analyze table or backup events. Yeah, and the dotted black dotted line denotes the resource capacity. Yeah, and the third scenario we face is there may be influx of data in a short period of time, and this may cause some nodes overloading. Yeah, so how to prevent the nodes from becoming overloaded in the event of a large data influx? Yeah, because one overloaded node may cause avalanche of the whole system. And the fourth part of the challenges is because there are more and more applications moving to the cloud. So we also hold our TiDB cloud service. And yeah, but on the cloud, you need to realize that all the resources are strictly limited. For example, the AWS CBS, the cloud disk CP3 has a 3,000 RPS and 125 megabytes throughput for free. But if you want to use more RPS or use more bound-wise, you need to pay more. Yeah, so the resources are limited on the cloud. And also, like for the 8-core EC2, there is instance. They have a 288 megabytes per second bound-wise limitation. Yeah, this is a hard restriction. Yeah. And there's another fact that if you run out of cloud disks IO quota, and you will facing the throttling of the cloud vendor from the cloud vendor. Like it will throttle your IOPS, your boundwise, and will let the IO latency increase extremely. Yeah, this is not a thing you want to see in your online service, especially TiDB as an online transactional and analytical database. So we need to keep everything under the quota. Yeah, this is very important. And this is a lesson we have learned in the past few years when we built our TiDB cloud service. Okay, let's come to the first issue. Is how TiDB handle traffic school issue. Yeah. From this picture, you can see this layer is stateless compute layer. We call it TiDB layer. And you can use MySQL protocol, like MySQL client or other MySQL protocol to connect to TiDB layer. And then you can send a request to our database. After TiDB received this SQL request from the client, it will route all of these queries to the storage layer, maybe read some data or write some data. And we use Raft to keep the data between different replicas consistent. Yeah, you can see there. You can see here we have region 1 and region 2 in our system. We call a data range a region. Yeah, and by default, each data range has 3 replicas. You can see here. This is one replica of region 1, and is another. And the third one. Yeah, so in this picture, there are 2 different data range, region 1 and region 2. They all have 3 replicas and placed on 3 different nodes. Yeah, and from this picture, you can see that the region 2 data range has received a lot of requests, and this will let this data range busy. Yeah, and I use the dark red color to denote. Yeah. And in TiDB, it will monitor the load of each data range and do some statistics like the request count and each request, how many bytes each request read and write, and what this request, the data range belongs to, like that. And then it will heartbeat the load statistics to the placement driver part. Placement driver is a metadata center of our database. Yeah. And then the placement driver part will make a decision that split this data range into several pieces and then balance the leader for the data to other nodes. Yeah. From this picture, you can see the previously region 2 split into region 2, 3, and 4. Oh, sorry. And you may notice that 2, 3, 4 has different size. Yeah, because I just mentioned, because we can monitor the request range. Yeah, and from this picture, you can see even in the same data range, the traffic also has some scroll issue. So we not just split this data range in the middle part, but we split it based on the load, based on the real-time load. Yeah. And by doing this, you can see the request may evenly to distribute to different nodes. After we did this, we made a simulation test for this feature. Let me explain more for this picture. At first, we simulated a hot rate range. And you may see at the beginning, at the workload beginning, there are just one node to handle all of these requests. And so its CPU may reach the capacity of this node. Yeah. And after 2 or 3 minutes later, the QPS goes up and all of these 3 nodes can handle the request. Yeah. One more explanation. For the vertical axis is exponential. And yeah, you also want to know how to monitor the traffic score issue in your database. Fortunately, in TiDB, we have a component named dashboard. Yeah, and there is a key visualizer section in the dashboard. You can monitor the hotspot or traffic score issue easily in this part. For example, the vertical axis means the data range. Yeah, which database it is, and the table, and even in the table, which index, yeah, this data range belongs to. And in the horizontal axis is the timeline. Yeah. In this picture, you may see there is a bright line here. It denotes there is a there is a right hotspot in this workload. Okay, let's move to the second part, smooth IO spikes.
Sorry, so can I assume that all the data stored in all the 3 regions, they are all the same data types?
Perfect.
They are all the same data types, like video data, code data.
Yeah. You can see most of the Yeah, all the data range here. Yeah.
Okay.
And if some data range is hot than others, and in this picture, it may be broader.
Yeah, that's right. Yeah.
And the next part is how TiDB smooths IO spikes and tag foreground IO with higher priority. Because we use RuxDB as our underlying database, underlying key value store in our storage layer. So if you are familiar with LS tree, you may know there's some background jobs like compaction and flash. Yeah. And these jobs maybe introduce a huge IO spike. Yeah. So we need to smooth this background IOs. Yeah. And also beyond the underlying storage engine part, in our storage layer, we also need to smooth the IO for all of these large events like backup and analyze your tables. Yeah. So we introduce the quota limit mechanism in our storage layer. You can set the background read and write boundwise and yeah, and other things like that. And also we tag the foreground read and write higher priority than the background jobs. Yeah, so the high priority tasks doesn't get blocked by the lower priority tasks. Yeah, this picture shows, the left part shows after we applied all of these smoothing optimizations, we can see the QPS and the latency is more smooth than the right part. The right part, we didn't apply these optimizations.
May I know whether there's any suggestion or best practice to set those values?
Actually, by default, it's on.
Okay, so,
Yeah. So for user, actually, you don't have to pay too many attention for this part.
Okay.
Yeah.
Good to know that. Thanks.
And the third part is how to prevent from overloaded. Yeah, we introduce the flow control mechanism based on the underlying engine state. Yeah. Before we dive into this part, I'd like to introduce the right ball of RuxDB. As I just mentioned, RuxDB is a LSM tree structure key value engine. And the write, at first it will write in the memory and also write in the WL, write a head log. And then when the member table or member buffer is bigger and bigger, it will flash to the disk. And we call this sorted table. Yeah. And as the SST files more and more, we need to compaction. We need to merge them. And this process is called compaction. Yeah. Because if you didn't merge them, you will tolerate the space amplification and the rate amplification. Yeah. It means the rate may be very slow, more and more slow, and the space will more and more larger. Yeah, and maybe most of them are redundant. Yeah. So RuxDB introduced a write store mechanism, and it will slow down the write, the foreground write, when the flash or the compaction cannot keep up with the incoming write rate. Yeah. But the RuxDB's write store sucks. Yeah, this is a picture from our production cluster, TiDB cluster. You may see that. Whoa, it will write store for more than 2 minutes. Yeah, even 4 minutes. Yeah, it's unacceptable.
Yeah. So okay.
Oh.
Yeah, there's a delay here.
Yeah.
Okay.
Okay. Yeah. Yeah. You can see that it may delay your write more than 4 minutes. It's unacceptable for the online transactional database. Yeah. So we cannot bear it. So we introduce our self flow control. And at first we totally we just remove RocksDB's right there. But just remove it doesn't work because the background compaction cannot catch up with the foreground write, and this will make the read latency is high. Yeah. So we also monitor the underlying engine status. Like we use a sliding window algorithm to monitor the average number of pending compaction bytes. Yeah. By this way, we can in this way we can tolerate temporary spikes of the underlying engines. So it will reduce the unnecessary like write store from the engine part. And after we monitor the status of our underlying engine status, we need to feedback this status to the scheduler, which is the entrance part of our storage layer. And if the scheduler, I mean the entrance part, has a feedback that the underlying engine is going to be overloaded, it's going to become unhealthy. Yeah, it will do something. It will reject some request to the compute layer to let the TiDB part retry it after a while. Yeah. But actually, in the real experimental test, it's far away from seconds. It's just like several milliseconds, 10 or 5. It's just okay. Yeah. So for the client, it's just all of those things are transparent for the client. Yeah.
So you're pushing the store to closer to the client. How is it different from spread store?
The RocksDB's write store is very rough. It's very raw for us. You can see it may stale for like several minutes, but we just smooth it. We made the entrance part can feel how the underlying engine what is the current state of the underlying engine. Yeah, and to do some like throttle.
Excuse me. So you are meaning like the TiDB has some metadata about storage thing, right? So you have about or you have an estimate about like how many things you are already under processing, so that you can just limit this spec as you just.
No. This part is just for the storage layer. It can recognize how large the throughput it can handle. Yeah, and then
So what if it's larger than?
Yeah. It will in the client part. You will feel everything will swallow in a smooth speed.
How do you define? How do you define what is smoother versus like more struggle?
Because our first goal is to provide predictable performance.
Yes.
So, if there are a large amount of data coming in a short time, we just make everything smooth. And let our engine always in the healthy condition.
Can we say that we set the threshold below the we set the threshold below the actual limit for which may trigger the restful. So let's say that if there's a for example 10 gigabytes of pending compact bytes, it will be restful. So we set the limit to probably to 8. Then we try to push back at 8, which RocksDB still feel fine. So the compaction won't cause restful.
Yes, it's kind of like a mechanism to particular escape the trigger of
because the problem is that the restful is really disastrous, right? And if once it is in the restful scenario, it's really difficult to recover, right? Then we have a headroom there to prevent from entering that.
So it's like it's chasing after the boundary of it. So you never reach it. Right?
It's like a back pressure thing. Right?
Yes.
Yeah.
Gotcha. Thank you.
Yeah, in my opinion, it's a mechanism to protect the storage layer. From overloaded. And second point is that the backoff and retry mechanism between the SQL layer and the key value layer is better than the rest style mechanism in RocksDB. So we leverage that mechanism to protect the storage layer.
So
that's
the meaning of like sliding window, right? Just need to smooth every incoming workload.
Yes, exactly.
And this just cannot deal with the consistent high load. If the high load persists, then everything will be okay. Right.
Nobody can. So
nobody can. So just spike.
It's fine. And nobody can really.
So we actually started dealing with the spike, not the consistent.
That it's not spooky. That will be still like a great progress at all. So.
Actually, we spend a lot of effort to build the backoff and try mechanism between the SQL layer and the key value layer. We handle more complex situations than rest stale. There's maybe network delay, latency, or tech KV nodes gone. So it's more sophisticated mechanism, in my opinion.
I can understand that the purpose of the matrix, the average number of pending component types. Just curious, does that threshold depends on the kind of backend storage, like whether it's a hard drive, whether it's a spinning drive, whether it's a flash drive, because they have different different cache.
I think so. Because the workload of the feedbacks is real time.
Yes.
Or
So you do have some metadata in PD, right?
We have.
Right. So you know how the hardware performance, how large can be, how my I/O throughput. So you can have based on statistics, you got the idea like how large workload I can handle. So I will never trigger the stall in the RocksDB, right?
Actually, in this part, we didn't involve the PD part because every technical nodes can know these things. And the PD part just balance the throughput across different nodes.
All right, thank you.
Okay, let's move on. And this picture shows after we introduced this part and we simulated a huge boundwise, and you can see the compaction pending bytes didn't go up, and it's under a safe level. Okay, the last part is reduce our usage by introducing Raft engine. Because I just mentioned that on the cloud, every resource has a strict limited. limitation. And if you want more, you pay more. Yeah. So how to reduce the unnecessary like IO usage is a very important work for we build our database on the cloud. And before we go to the Raft engine part, I'd like to use the Raft log in TiDB, because I just mentioned that every data range in our TiDB, in our storage layer, has 3 replicas by default. And we use the Raft algorithm to make the data consistent across different replicas. And you can think, simply think the Raft log, just the read log in other databases. Yeah. And the write process is like that. At first, a write come in and we need to write a Raft entry, Raft log. And in the Raft entry, we contains the operation you will made for the database. And then after the majority of the replica has received this Raft entry, we can apply this Raft entry to the database. Yeah, and then we need to delete the Raft entry. So you may find out, you may notice that the Raft entry or the Raft log has a sequential write and the sequential delete. Yeah, characteristic. But as in the early days, we want to deliver our database fast. So we use the mature key value store RaxDB to store this part. I mean the Raft log. Yeah. And but you know, RaxDB is a general purpose key value store, and it's a LS tree structure. Yeah. And actually, it's not optimal in the sequential write and the delete workload. So this will introduce some unnecessary like write amplification, yeah, to our system. So, and then we introduced our self engine. We call it Raft engine to store our Raft log. Yeah. We just you can just think it's a log app data store. Yeah, because everything is sequential, and for each data range, there are 2 components. One is memory table, we call it memory table, which we will hold the all the entry index that keep track of all active log entries. Yeah, and it's like a pointer the position of the log entry in the log file, and the log file the file part is just a append only log file. Yeah, and because you know we apply the Raft entry one by one in order, so after the order one has applied to the database, we can remove that. But previously in RaxDB, we need to write the delete to the RaxDB. In RaxDB, delete is also a kind of write. Yeah, and we'll also introduce some IO. Yeah, and in our Raft engine, if there's no Raft entry pointed to the file, and this file can be removed. Yeah. So for the delete part, we didn't introduce any IO. Yeah. So this is the main this is the main mechanism of our Raft engine. Yeah.
So can I say it's a general purpose log store? Can I use it in other scenarios other than?
Yeah.
Cool.
Actually, we this Raft store we also are inspired by like PingCAP, like that. Yeah, it's also a log at data store. Yeah.
So when they say memory table is in memory.
Yeah.
How come, like, for example, if it's lost in like a crash,
yeah. And you just when the attack restart, you just go through this log files, because every region will not keep too many logs, because after you apply this change, you will remove this log. Yeah, so it's small.
So you can review.
So actually, I know, like it does have some content like LSN, something like that, right? LSN in like MySQL, whatever. So.
Yeah, like that.
Yeah. So you have some sort of like ability to sequence yourself rather than.
Because we use there is a meta file to record the active logs like that. Yeah.
So another question, like how can the like read performance compare with the originally the RuxDB, right? Because right now you are doing. Suppose I'm already done customer.
Yeah. Actually, we use buffer. So the latest write maybe still in the buffer. In the buffer. So because we just need to read the latest several entries. Yeah.
A normal pattern is like you will just read. You doesn't read code data. You just read hot data.
Yeah. This is the
cache, right?
Yeah. This is
But we still can have an assertion that if you are somehow read the code data, it will be lower than.
Yeah, this is just happen when you like restart your nodes, and because when you restart a node, there is a period that this node didn't provide service. Yeah, so it's okay.
Yes, but
yeah. So I think question is that for like reading the code data, I think compared with RuxDB, I think the Raft
it also
should be faster or
faster.
smaller.
Yeah, faster.
I think it's more faster.
Yeah, because it's just a sequential read, and just you can think it's just one level.
It's a purpose-built storage.
Okay, it's just one level, but RuxDB has several levels. You need to read data from several files and merge them. Yeah.
So it's still like a WAL, right? So rather hand log, something like that. But it's in the log format, so basically it's our storage, something like that. It's sort of like an SST. Yeah.
Just one level.
Maybe one level. Yeah. Thank you.
Yeah. And this is the test result of after we introduced the Raft engine. And we use the TBCC benchmark, which is a classic online transactional workload. And you can see the right bound-wise, we have reduced is around 30%. Yeah, this is a big improvement, I think, especially on the cloud. Yeah. Okay, let's move to the last part, future work. The first one is QoS. Quality of service. Because as a distributed database, TiDB has many adoptions, and many of the customers previously they have more than 10 or 20 applications in one company, and they may use different individual like MySQL instance or Aura instance to store the data for one application. But there may be 20 or 30 applications in one company. So they will facing they will need to maintain 20 or 30 MySQL instances. So if there is a distributed database, why not just use one distributed database? Because distributed database has a great scalability. You just need to add some nodes. Yeah. And compared to maintain so many MySQL instances, you need to like do the daily backup, do the upgrades. Yeah. So many of users use TiDB as a data service backend, and multiple applications can use the same TiDB cluster. But multiple applications to share the same TiDB cluster, we will face the challenge that how to guarantee each user can experience a predictable latency and performance. Yeah. So this is the quality of service part. And the second future work is the flashback. Previously, we have a feature called flashback. And if you delete or drop your database or table by mistake, and you can just input one command, flashback, and you can get your database or your table back in a few seconds. Yeah. But also we we have some gaming users gaming. In game, somebody may do some like fraud, and this will let the data in the database go wrong. Yeah. So if you are a like gaming vendor, you maybe want to roll back such operations. So how to roll back the existing cluster to the state of like 30 minutes or 1 hour ago? Yeah, this is a real world feature request. And the third one is we will continuously improve the speed of data balancing when scale in and out of our database. Because the data is more and more larger, and the nodes is more and more. The number of nodes also more and more. So how to scale fast? That is a challenge for us. And also, as the nodes are more and more, and how to improve the high availability when there are 1 or 2 or 3 nodes goes down, crash. Yeah. And also, we need to improve our resource control mechanism, like how to control the global memory usage, how to mitigate the background job, like the batch job, like delete a bunch of data that actually it may have some impact for this online service. So if you are interested with all of or some of these topics, feel free to contribute to the repo I just listed here. And most of the part of our code is open source. Yeah. So thank you, everyone. And I think we have come up to the end. And let's move to the Q&A part. Feel free to ask any questions online in person. Is there any online questions? Let me check.
Oh, thanks, Jinpeng. There's currently no questions online. So is there any questions in the meeting room?
Yeah, I think we have talked about many questions.
Okay.
But
cool.
Also, yeah.
I don't think I have actual more questions.
Okay.
I don't feel like I'm the most more person who have more questions.
Yeah, you are the part of this talk.
Yeah. definitely.
I'm honored. Thank you.
Okay. Okay, thank you for coming and in person and online. See you next time.
Yep. Oh, and Jinpeng, do you mind let me share my screen?
Yeah, last thing. Yeah, for the
one
speaker.
after.
Yeah, we have a special spec for the speaker. Yeah, it's a fashion photo, and yeah, you can see.
You can have a tour next time.
Here's a SQL. Here's a SQL here, and for anyone who would like to deliver or talk here, you can earn this special spike. Even our CTO needs to deliver a talk to earn this. Okay. Okay. Yeah. Thanks, Jinpeng.
Thank you.
Yeah.
Thank you. Thank you, everyone.
Okay. Okay. Thank you, everyone. So, two last slides I would like to go through. The first one is welcome to join our groups. We have WeChat group, we have Slack community group, and you're also welcome to sign up TiDB Cloud. And if you want to learn more about TiDB, we do have different courses, including TiDB Technical Essentials and TiDB Architecture Basic. Cool. That's everything from my side, and thanks for coming.